We'll So welcome everybody, and thanks for being here tonight. Omar, Ray, thanks for being on Zoom with us. Just wanted to kick us off. This has been an interesting month, solar or lunar eclipse and a handful of other things, but we actually have. I'm sorry. Sorry about that. We actually want to launch into the talk that we have tonight. We actually have a very interesting talk from Dr. Kacper Weirzchos. I'm sorry if I butchered your name, sir.
It's okay. It's good. Good
Yeah,
enough.
yeah. From the Catalina Sky Survey, and frankly, one of the comets that carries Dr. Weirzchos' name is in the sky tonight. So I've been imaging it over the early part of the month and could share a picture a little bit later, but appreciate everybody being here. And Eric, I'm going to turn it over to you for an introduction, and then we'll go into the talk, and we'll follow up with our normal process of announcements after we complete with our speaker. So again, thank you, sir, for being here. And go ahead, Eric.
Thank you. Our speaker today is Dr. Kacper Weirzchos. He was born in Poland in 1988, but spent most of his adult life in Spain, where he got his Bachelor of Science and Master of Science degrees in applied physics. In 2015, he moved to the USA, where he completed his PhD in applied physics with concentration in astrophysics at the University of South Florida. His dissertation focuses on comet activity and at large heliocentric distances detected with radio telescopes at millimeter and sub-millimeter wavelengths. In 2019, he joined the Catalina Sky Survey as a senior survey operations specialist. And since then, he has discovered hundreds of near-Earth objects and 7 comets that bear his last name, the most famous being Comet 2024 E1 Weirzchos. And also, when you get a moment, go on to YouTube, look up his name, and you'll see some great guitar songs that he's playing on YouTube. Take it away, Doctor.
Okay. Thank you. Thank you for the introduction and thank you for inviting me. Let me see if I can share my screen.
Let me stop my share, and you can reshare now.
Okay.
I want to remind you, if you are sharing anything with audio, there should be a checkbox to include audio with the sharing.
Okay.
Are you recording? We're recording, yeah.
So now I'm gonna share my screen. Share. No. Okay. Can you see my screen now?
Yes. We can, yes.
Perfect. So I'm going to make an introduction to the Catalina Sky Survey and how it works, what we do to discover near-Earth objects and comets. So we cast a very wide net to the sky, and we see pretty much everything that moves within a given magnitude range and a given motion range. So we are based at the University of Arizona, specifically at the Lunar and Planetary Laboratory, and we are funded by NASA's Planetary Defense Coordination Office. So why planetary defense? Well, in 2005, the Congress of the United States tasked NASA with finding 90% of objects in our solar system that are near-Earth objects that are 140 meters and larger. So basically, we are following that mandate, looking for near-Earth objects. And things like comets, centaurs, trans-Neptunian objects are a bonus. But comets are very dear to my heart because that's my specialty as a scientist. So let's first talk a little bit about near-Earth objects. So near-Earth objects are near-Earth objects or near-Earth asteroids. They're also near-Earth comets. Are basically objects in our solar system that have a perihelion distance smaller than 1.3 astronomical units. So far, we have discovered over 41,000 as the community, and this number is expected to be much larger in the near future because of Rubin and projects like NeoSurveyor. CSS has discovered over 17,000 of these objects, and tens of thousands still need to be discovered to complete that mandate that Congress gave to NASA. And a fun fact is that near-Earth objects can impact Earth, as we have seen. So asteroids are basically, they're like irregular. They have different shapes. Some of them are contact binaries. Some of them are actually binary asteroids, the main one with like a moon. And for our purposes, we tend to talk about them between being 1 meter and 35 kilometers in diameter. They tend to be porous, and they're like, or they can be solid. They can be like purely metallic, but they can be also like a rubble pile with very low surface gravity, as we've seen with projects such as OSIRIS-REx. And they have composition that can vary wildly. This is a really neat animation made by Scott Manley, I believe, that showcases the discovery of objects. So, as you can see, as the Earth moves around the Sun, we are discovering most of the objects in the direction opposite of the Sun. That's what we call the opposition region. So when our moon is in the direction opposite to the Sun, what do we have? Well, we have a full moon. So same happens with asteroids. And why is that? Well, because of the phase angle effect. When an object is at opposition, all of its area is reflecting sunlight. And that is also why objects discovered at very low solar elongations tend to be big. So you could call it an observational bias, because the objects that we see at low solar elongation have to be big because of the phase angle effect. Make us always see like a sliver of light, same as the moon when it's just waxing, or what's the other word in English? Sorry, gibbing. Like when the moon is like a thin sliver, that happens at low elongations. So same with asteroids. So near-Earth asteroids can be classified into 4 main classes. So we have Apollos, which make up most of the near-Earth object population. You can see here a representation of the typical orbit of an Apollo. We then have Amors that never actually cross Earth's orbit. We have Athens that spent most of the time inside of Earth's orbit. And we have Atiras, which there's only about 40 known Atiras. Those are objects whose orbit is completely contained within the orbit of the Earth. And the most interesting objects, the ones that we call them the ones that pay the bills, because those are the ones that NASA is the most interested in, are called PHAs, or potentially hazardous asteroids. So those are objects that have a size of 140 meters or larger, and in terms of operations, we look for the absolute magnitude of those objects to be 22. So if an object has an absolute magnitude smaller than 22, 21, 20, 19, etc., that means it's a large object. So a magnitude of 22 using the average albedo for an asteroid is equivalent to 140 meters. And the other condition that an asteroid needs to meet to be considered a PHA is that it has a MOID, or what that stands for is minimum orbit intersection distance with Earth's orbit of 0.05 astronomical units. That means that those objects get quite close to Earth, relatively speaking. So currently there are just slightly over 2,000 known PHAs. So let me show you here. I can show all the types of, there's one more, Atiras, there we go. All of the near-Earth objects, the different classes. But there's probably a factor of 10,000 or more objects contained within the main belt. So there are different orbital processes by which a near-Earth, a main belt object can become a near-Earth object. They mostly have to do with gravitational interactions with Jupiter and sometimes even with Mars. Oops. Oh, there we go. So these are recorded impact structures in Earth. Some of them have, of course, very visible craters, like we'll know about the Arizona, the meteor crater. And some of them are very old, and those structures have been buried or masked by geological processes, so it's very hard to detect them. So basically, the reason why I wanted to show this slide is to say that asteroid impacts with Earth are a natural geologic process. It's something that has happened in the past, of course, with a higher frequency, and it's something that will happen in the future. As of now, we don't know of any asteroid that poses an impact threat to Earth in the next 100 years. So we are safe, but anything could change tonight if someone discovers an asteroid that might pose an impact threat to Earth. I forgot to say that there are 3 main asteroid surveys. 2 of them are located in Hawaii. They're called Pan-STARRS and Atlas. And then the other one is where I work, which is the Catalina Sky Survey. And those 3 surveys are responsible for well over 90-95% of the yearly discoveries of near-Earth objects and also comets. So the most famous and recent case of an asteroid producing damage to Earth, at least human-built structures, was the Chelyabinsk event in 2013. If you can look it up on YouTube videos about the Chelyabinsk event, and you'll see what the explosion of this object in the atmosphere, what the shock wave did to the city of Chelyabinsk. There were over 1,000 people injured, mostly due to broken glass, falling debris from building. And it was just a 20-meter asteroid. So that is not a big asteroid. So imagine what a bigger one could do. Also, we got very lucky with the fact that this object had a very shallow trajectory when it entered the Earth's atmosphere. It was going it was going basically horizontally. If it went perpendicularly to Earth's surface, it would have way less atmospheric, the layer of the atmosphere through which it will go would be much thinner, and there is a very good chance that it would have caused a crater and a massive explosion, and things would have been much worse for the people in Chelyabinsk. The explosion of this object in the atmosphere was roughly equivalent to 30 nuclear bombs like the one dropped on Hiroshima. Another recent event, and I want to talk, when I say recent, I mean by planetary or cosmic scales, so just slightly over 100 years ago, so that's very recent. It was the Tunguska event, which was an object that also entered Earth's atmosphere, exploded in the atmosphere, and it had an extreme energy of roughly 10 to 15 megatons, equivalent to TNT, so roughly 800 times the blast of the nuclear bomb dropped on Hiroshima. And this event flattened roughly 2,000 kilometer squares of forests. So there are many images of basically trees falling in a radial manner. So basically trees laying down radially towards, basically pointing towards where the event took place in the atmosphere. Well, I don't think I need to talk about what happened to the dinosaurs, but well, we all know what happened to the dinosaurs, and that was a very large object, roughly 10 to 15 kilometer in diameter, and it made a massive crater that it's still detectable through different means. It's not very obvious, but also made things like the cenotes in Mexico, and even the sweetwater, the freshwater springs in Florida, for example. That is all due to limestone formations that were caused by this event. And well, it wipes out over 70% of the plant and animal life on Earth. So let's talk a little bit about how do we actually search for these objects. What is our mission? Let's talk about the operations. So we currently operate telescopes on two sites, and a third site also in a collaboration with the Spacewatch Group and the University of Minnesota. But this is where our main telescopes are located. They're on Mount Lemmon and Mount Bigelow. So they are situated on these peaks in a range called the Santa Catalina Mountains, which is basically the mountains that are at the outskirts of Tucson, Arizona. And lucky for us, Tucson has always been very respectful of astronomers, because there is a very big astronomy community in Tucson, and there's four major observatories around Tucson: Mount Lemmon, Mount Graham, Kitt Peak, and the Fred Whipple Observatory on Mount Hopkins, where the multi-mirror telescope is located. So that, not only the science that is being done with these telescopes, but also the support, technical stuff, the people at the Mirror Lab. Basically, it's a big source of income for people of Tucson. So they have strict light pollution laws for a city of the size of Tucson. So we use two survey telescopes mainly. There's also that third one that I mentioned with collaboration with Spacewatch. And basically our flagship telescope is what we call the 60, because it has a mirror diameter of 60 inches. And with this telescope, we discover over 90% of the NEOs that we discover every year. And how many is that? Well, slightly over 1,000 NEOs a year. This telescope, the 60, hits the sweet spot between reaching a deep enough magnitude and having a good field of view. It reaches on a good night magnitude 21.7 in a 30-second exposure. That is if moon is not present. And the Schmidt telescope, it's a converted Schmidt camera, can only reach down to magnitude 20.5-ish on a good night. but it has a massive field of view, much bigger than the 60. And then we have two telescopes that we do follow-up with. So just so you know, whenever a new near-Earth object is discovered by us in real time, and by that I mean I'll show you a picture where we sit and where we do this work, we send this object in real time to the Minor Planet Center, but it has a very short observation arc. That observation arc is just the time between the first and the last image taken by the telescope. So there is virtually an infinite number of orbits that can be fit through those 4 points. So we use follow-up telescopes in order to refine the orbit that same night, so that we can recover that object on the next night and so forth. And then there's a point at which the Minor Planet Center, which is the clearinghouse for observations of near-Earth objects and comets, there's a point at which the Minor Planet Center decides that the orbit is good enough to announce the object. So on the right we have the two telescopes that we use for follow-up. The Kacper, which is 1.5 meters in diameter, and then the 1 meter. This is a comparison of the field of view of our Schmidt telescope. It has 19.5 degrees square. It's very big. And we are able to survey the entire visible sky from our latitude, roughly 12 times per lunar cycle with this telescope. It can be more or it can be less, and that depends, of course, on weather. And that telescope and its software, it's fine-tuned for bright and fast-moving objects. And on the right, we have the field of view of our other survey telescope, the 60-inch. Has a smaller field of view, and we try to cover the entire observable sky roughly 1.5 times per lunation, depending on weather. And this telescope and its software it's fine-tuned more towards the objects that are dimmer and move slower than the Schmidt. Let's see. Oh, okay. So just a few pictures of the 60-inch. That's my colleague Greg Leonard there on the left. The dome, and you see the telescope. It has an equatorial mount that it cannot point into the north. You can see that it's limited by where it can point to the north by the design of the equatorial mount, and that is because this telescope, as well as the Schmidt, were originally built to study solar system objects, and the vast majority of solar system objects have lower inclinations and are close to the plane of the ecliptic. So, if we exclude things like comets with high inclinations or retrograde orbits, we don't need to look high up north. This is our Schmidt telescope. Same, you can see that the mount limits its pointing capability towards the north. And you can see the dome to the left, the dome to the right. It's also, it's funny because in the Santa Catalina mountains, we actually have an alpine climate, whereas in Tucson, Arizona, we have a desert climate with saguaro cacti. So in the space of 1 hour, you can drive from the desert to an alpine region with basically with snow in winter, as you can see. So this is how the workstation works. This is where the person, the observer, doing the work at night sits. We have 6 screens. We have experimented with a few more, a few less. Anyway, this is like a good balance of that we can have displaying all of the software that we need to do the job. And on that red telephone, it's just a normal telephone. It's not connected to the White House, but we bought it especially because we do planetary defense, and when there's like a visitor or something, it looks so cool to have an old school red telephone. Okay, so what you see here is a software called CovTool, or what we call it a coverage tool. So basically, this is our in-house version of a planetarium software, but it was made by us in-house, and it's basically it covers all of our needs. So you see there are these colored boxes here. There's like a pink one, there's like a yellow one, a green one, then a blue one. So that's what we call a set, or a survey set. So how does this work? What do we actually do? Well, we take 4 images of every field in a set, and a set can roughly has about 12 images. So we take one image of a field, then we move to the next, 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 and then we come back to the first one, and then we repeat that process until we have 4 images of the same region of the sky. So what do we do with those images? Well, as I said, the telescope plus the camera take 4 images of one region of the sky, of one field, which is part of a set, and then we have it's like a computer farm. Like, we don't need heating sometimes in winter because of how many computers we have processing this data, and we have several computers that do several functions, but of course we have to do things like image calibration. This is all streamlined and it's done automatically. Flat field, subtraction, that sort of thing. We plate solve the images, of course. Then there is a software that we use that basically subtracts the stars from from a field after it's been plate solved, and looks for things that are not stars that have motion. So basically moving object detection. Then also we have to have a way of identifying known objects in a field, because on a field close to a position, I have seen over 400 known asteroids in a single field. That's like a very large number of known objects. And then ultimately the software identifies this new candidates, new asteroid candidates, after it has subtracted the known asteroids. And that's where the human comes in. The human sits in front of those computers and will look at these moving objects and make a call. Is this a real object or is this some sort of artifact? So basically we blink those images. We make like a 4 frame movie. 1, 2, 3, 4, 1, 2, 3, 4, and we decide, is this a real object? Is it involved with a star? Is it a diffraction spike? Is it a flat field artifact? Is it an artifact at the edge of the field? There are so many ways an object cannot be real. So basically we identify real versus false detections, and when we send the candidates of the new objects in real time, as soon as we identify them, to the Minor Planet Center, and then the person running the follow-up telescopes will perform follow-up observations. So we have 1 person per telescope. So in a given night we can have 5 people working, and we are in communication to coordinate things like follow-up, survey plans, because it's CSS is unique in that regard that it does survey and follow-up, so it's like an ecosystem within the larger ecosystem of planetary defense. On a given night in winter, when the nights are so long, an observer will look well past 6,000 images by eye and make 6,000 decisions whether an object is real or not. So here we see an object moving. Can you spot it moving?
Yes.
You see it? And that's a telltale. That's a telltale that this is a real object, because it's streaked, and it's streaked in the direction of motion. So basically the object moved while the exposure was taking place. And that object, there you go. Yep. Yeah. That object was actually 2018 LA, which is an object discovered by one of our observers, Richard Kowalski, and it was an impactor, basically an object that was discovered before entering Earth's atmosphere. There have been, I think, 9 impactors found so far, and like 70% of them, so 6 of them were found by our group, the Catalina Sky Survey. And luckily for us, they all have been small, 1 meter, 2 meters in diameter max. So they just burn up in the atmosphere, they make a beautiful fireball, and that's it. And then some people are actually able to recover fragments of them. Let me see. So one of the greatest hits of CSS was the discovery of 2008 TC3, which is an object that also Richard Kowalski from CSS discovered. And it was the first object in history to be discovered before impact with Earth. It was roughly around 4 meters across. It disintegrated in the atmosphere over the desert in Sudan. And people were able to find those objects. And here we have a picture of Rich Kowalski holding a piece of the object that he discovered with the telescope, which he discovered it in the background. So it's like a really cool thing. It's a meteorite known as a Malta Zeta. And so Rich basically is the first person in history to discover a celestial body and then actually have that part of the celestial body in a box in his house. So as you can see, the near-Earth discovery rate increased exponentially after the adoption of CCDs. You can see here that from the 1980s up until CCDs became the norm, roughly in the early 2000s, the discovery rate of near-Earth asteroids was, well, it was so small that we would really have to zoom on this plot to really see it. Now, when the CCDs came into play, that's where the fun began. So we can see an exponential growth, the discovery of these objects. Blue, oh, sorry. No, there we go. Blue are known, are all asteroids and all near-Earth asteroids, and orange are asteroids bigger than 140 meters in diameter, and red are objects that are bigger than 1 kilometer. It is safe to say that we have discovered well over 99% of the objects that are 1 kilometer in size or more. But I'm talking about near-Earth asteroids. If we start talking about near-Earth comets, that's a different story, because as we know, comets come from very, very far away, and we only discover them when they are closer to Earth. Here we have a plot with the discoveries by different groups since 1995, and in green is the Catalina Sky Survey, pink is Pan-STARRS, the other survey that I was talking about, and blue is Atlas, and this brown bar that says other US, that is mostly also us, but in collaboration with Spacewatch from Kitt Peak using the BOC telescope, the BOC 2.3 meter telescope. Well, so we know that asteroids, near-Earth asteroids, are a natural geologic process on Earth, and we have tested a way to at least change their orbits, to slightly deflect it. So a kinetic impactor with an object that was discovered early enough would just move it slightly out of its nominal orbit so that it would no longer impact with Earth. So of course we all know about the DART mission and how it changed the orbit of a moon of asteroid Didymos, and it was a complete success. It's the first test of this kind ever performed in history. So well, now at least we know that the kinetic impactor method works, at least for these sizes. Yeah. So basically, there are serendipitous discoveries. As I said, we are funded to discover near-Earth objects, NEOs. But we have discovered in total over 340 comets. And they are serendipitous discoveries. They're a bonus. They're a bonus which I love because, as I said, as a scientist, I'm a comet specialist. So I just, I don't know. I just love comets, and for me, it's almost the most important part of the job, even though it's not our mission. We have also discovered TNOs, trans-Neptunian objects. Main belt asteroids, we're not keeping count, but it's tens of thousands that we have discovered over the years. We have discovered 2 mini-moons, so objects that were in an orbit around the Earth-Moon system. Those orbits were very chaotic because of, well, it's a three-body problem. And we have discovered impacting space junk, and we have also seen Elon Musk's Tesla that he launched, I don't know, a few years ago. So now I hope you can pardon my vanity by showing what I consider my most meaningful discovery, which is Comet C2024 E1 Weirzchos. It's a comet that I discovered back in March of 2024, and due to its orbit, we knew that it could be a cool object, not a naked eye object, but what we call a single-digit comet. So a comet whose magnitude was in the single digits. This comet, it's kind of weird because it has 4 tails. Usually comets have 2 tails, an ion tail and a dust tail. This had 3 dust tails and 1 ion tail. And this is probably my favorite image of this comet, next to NGC 55. Yeah, that's the galaxy. So the way we discovered comets is the same way we discover NEOs. Basically 4 images of a field contained with a set, blink, and then if we see an object that has an obvious coma or a tail, then we will report it as a comet, and then it will carry our last name. If we fail to see that the object has coma, because when a comet is magnitude, let's say 21.7, and that's the limit of our telescope, we're literally looking at like something that's 2 pixels across, very low signal to noise ratio. It won't show a coma or a tail, so we report it as a new asteroid. And then maybe 2 months from the discovery, someone finds a coma or a tail, and it's established that it's a comet, and then the comet is called Comet Lemon. That's why you'll see many comets called Comet Lemon. That means the discoverer the person was not able to identify cometary activity at the time of the discovery. And yes, this is my last slide, and I am open to questions, should you have any.
I do.
Yes.
This work?
Yep.
Howdy, my name's Jeff.
Hi, Jeff.
A few slides back, you showed an object coming into Africa, and I didn't catch the name of it, but I saw the date was 6/2/2018.
It was called 2018 LA.
Yeah, right. Okay, right there. So what I'm looking at is, I know the Earth and the other planets orbit the sun counterclockwise as viewed from the north. This one looks like it's coming in clockwise. Does that mean it's not a solar system object?
No, it is a solar system object, but it's very small. It was like a few meters across. And objects that are very small, like this one, can come from any direction. Those objects are debris from the formation of the solar system, and they're like flying in all directions. That's the thing with NEOs. NEOs don't necessarily adhere to the normal NEOs don't necessarily adhere to the ecliptic plane and the low inclination. The NEOs can be retrograde, can come from all different places, and the smaller they are, the more of them there are billions and billions of them. Of course, we don't discover them as much because they're small and far away, thus they're too dim for us to find.
Thank you.
Sure.
Doctor, thank you. Fascinating talk.
Thank you.
I'm curious, where the 140 millimeter size came from, only from the perspective that you shared that the Chiblinsk object was 20 meters. So 140 meters is, or the destruction that could come from that would be massive.
Yeah.
But is it a function of the size and the ability just to detect?
So that number came from Congress, and it's a number that wasn't that I would say didn't have a very solid basis. Like, why not 120? Why not 50 meters across? So it was decided that way in 2005 by Congress, and that's the way it is. There are talks about shrinking that number, about making it smaller, because we know that even objects that are much smaller than 140 meters can cause damage. So yes, there are current talks about reducing that number as the important number, so to speak.
Dr. Weirzchos, excellent presentation. Thank you very much.
Thank you.
The new Vera Rubin telescope and its sky survey, will it essentially do the same work that the Catalina sky survey is doing, or will there be a difference between the two surveys?
Well, there are many differences. So the Rubin telescope is a jack of all trades. That the Rubin telescope, it's not a near Earth survey. That's a telescope that's searching for sky transients. So basically, anything that appears in the sky, whether it moves or not. So supernovae, novae, like mapping, making a map of galaxies far away, things related to dark energy. So their observation cadence is not optimized for near-Earth objects. It's optimized to do everything that the LSST stands for, which is the Legacy Survey for Space and Time. So they're basically dipping their toes in everything, and they will reach much fainter than us. They're located in the southern hemisphere. So even though there are a few degrees of declination of overlap between us and Rubin, the northern part of the sky still will belong to us in a way. So yes, we expect a dramatic increase in the discovery of near-Earth objects. And yes, it will probably affect us. But we have, discovery is only part of the equation. The discovery without follow-up is nothing. The object gets lost, not confirmed, never gets a name, never gets an orbit published, So we are currently in the process of expanding also our follow-up capabilities. In fact, I'm the principal investigator within CSS. I'm not the PI of CSS, but within CSS, I'm the PI of our Find Follow-up program, meaning I write proposals, take data, analyze data of the largest telescopes on Earth. So I'm talking Gemini, talking LBT. So, like LBT, so it's a binocular telescope with each mirror being over 8 meters in diameter. So follow-up is just as important as discovery. And those NEOs discovered by Rubin will need follow-up.
I see. Very good. Thank you. And earlier you showed a slide of the various world impact sites.
Yes.
Could you go to that slide, please? Yeah. And I want to almost identify some kind of pattern in the locations.
Oh, what happened? Sorry. Wait. Can you see my...
We see your desktop.
Yeah, why is that? Oh.
There we go. We see it now.
Okay, perfect. Sorry about that.
So my question was, those impact sites almost look like they're predominantly in the northern hemisphere and of a certain latitude band, but I'm trying to discover or determine any other pattern, or what patterns, if any, have you been able to determine?
That's a very good question, and unfortunately is one that I cannot answer because I'm not a specialist in, in impact cratering and alt impact craters. So maybe there is a pattern. May also be about funding. Like if someone's going to do a survey, they will concentrate in North America and Europe, and Africa will not get as much, funding to do that sort of work. So that may be one reason.
Thank you.
You've got more land mass in the northern hemisphere than the southern hemisphere.
Okay.
That's true.
And part of Africa kind of tough to get to.
Well, it looks like there's a location bias because if you look at Australia,
Yeah,
so it may be population biased or something like that. Yeah.
definitely.
Where, you get to the less densely populated areas, they're just not discovering or.
Yeah,
Right.
could very well be.
Yeah. I've got a question for you.
Yeah.
A couple of slides after this one, you talked about the survey and that you take a section of the sky and then you go back to it 4 times.
Yeah.
There, that one right there. What's the time delay between the 4 shots that you take?
With our flagship telescope, the 60-inch is about 27 minutes,
Okay.
meaning that any discovery will have an arc of roughly 27 minutes. With our Schmidt telescope, is closer to 12 minutes
Okay.
because we use 14-second exposures with the Schmidt to cover more ground. Yeah.
That's what I was wondering. Oh, thanks.
Yeah.
I have a question.
Yeah.
Are there any programs for like citizen science to analyze data, help, break up the chunks and look for
Oh
the
yeah,
most?
it's called the Daily Minor Planet, and it's a program at the Zooniverse, and it's a program that goes through CSS data, and citizen scientists, amateurs, people can make significant contributions. In fact, many of them have been part of discoveries of near-Earth objects and also main belt objects, and they appear as measurers when in the official Minor Planet Center electronic bulletin and circular. So they appear as measurers, So if you're part of that project and find something, your last name will be published in the official announcements of those objects. Oh yeah, it's called the Daily Minor Planet, and I encourage you to take a look. And yeah, so it's basically our data. It's data that we cannot review because we're human and we have a limit. And reviewing 6,000 images in a night, there are many more detections down the list, but it's just we're limited to the ones with the highest probability. But yeah, so those detections that we don't see are presented to people in that program at the Zooniverse. Yeah. And I forget how many objects they discovered, but there's been quite a few.
Very good.
Yeah.
Would you mind also kind of explaining the naming convention behind the different objects that are found? Like what do the numbers mean, the letters mean, all that kind of stuff?
Yeah, so let's see. So it's a bit of a complicated no. Okay, so when an asteroid is discovered, an object is discovered like this one, you see it has a name 2018 LA. So 2018 stands for the year, and L stands for the month. So for half of the month. So the first half of January is A, second half of January is B, first half of February is C, second half of February is D, and so forth until L. I don't know which month that would be. And then the letters, you start putting letters. A, so that was the first one discovered in that first half of the month. And then you start putting in numbers, because like you run out of space, so you need to start giving them numbers. So, like 2008 TC3, So basically, that's the convention for objects that are discovered in one opposition. When an object is discovered, when an object is recovered on the second opposition, then that object can be numbered. It will get a permanent designation, and that is a string of numbers. The year is no longer there. And when an object is numbered, the discoverer has the rights to name it, to give it a name. And there are certain rules about not naming objects after political figures, after military leaders, unless they've been dead for like how many centuries. Then there are rules about the orbit, like for example, Ennius can only be named after Olympian gods and Olympic athletes. It's like a whole, it's like a whole thing. But yeah, main belt objects are the most common, and where most people, when they have an asteroid named after them, they're usually a main belt object.
Very good. Thank you.
Yeah, same with comets. C just means comet / non-periodic comet / 2024 discovered that year. E just means first half of March. 1 means the first comet discovered in the first half of March of a year 2024, and it's not a periodic comet because when they're periodic they have a P instead of a C.
Thank you.
This is Jeff again.
Hi.
If your system discovers a near Earth object in February, and then later on in August, I discover a comet and report it to Harvard, and then it turns out that they were the same dot, is it not going to be Comet Baldwin? It's going to be Comet you guys?
So the rules for nomenclature of comets are quite long, and they are, I don't want to say they are open to interpretation, but they have gray areas such as this one. So it will for sure have the name of Lemon, if it was discovered by our telescope and we did not see activity, and there is a chance that it will have also your last name, because I assume you are an amateur astronomer, not professional, right?
Yeah.
Yes, so the rules are a little bit different for amateurs and professionals. They're much more stringent for professionals, as it should be, and they're more lax towards amateurs. So they will make a vote at the International Astronomical Union, WGSBN, so that's the working group for small body nomenclature. They will take it to a vote and decide on a name. That's what
Can
they
they be
will happen.
bribed?
They cannot be bribed, and no, and you cannot name asteroids for monetary compensation, for example.
Well, like when an amateur discovers a comet, it's usually somewhere around magnitude 13 or 14. You guys are picking them off at 21, but you don't know they're a comet yet. And
Well,
later on, it's discovered as a comet. So I didn't know there's some kind of.
well, and then it's called Comet Lemon. That's it. That happens all the time. That's why you see Comet Lemons, because we found it, but we were not able to spot activity. In order for an object to be named after a person like me, working in a professional survey, I have to discover the object, notice activity, that is either a comma or a tail, and report the discovery. And I have to be alone in the building. Like, yeah, those are like rules, literally. So if there's two of us in a building, then it's automatically called Comet Lemon, not two last names. It's just, I didn't write those rules. It's just the way they are.
It seems that between this system And that huge survey scope going in the southern hemisphere, the day of backyard comet discoveries is probably over.
You know what? It's not. That that that's the story that we've been hearing for God knows how many years. You know, like oh, the professional. Yes, it's harder. It is harder, but every year, every single year, there's at least 4 amateur discoveries. In fact, my good friend and co-worker David Rankin, he's so passionate about this that he runs an 11-inch Celestron Rasa in his backyard in the middle of Tucson and does survey when he's not working, and he found a comet. So that is considered an amateur discovery because him, despite being professional, he was using amateur equipment from his home. You know, so every year you will see amateur discoveries, but the amateurs need to keep up with the latest in technology, and by that I mean software, specifically Tycho Tracker. If you're not using,
Well, it looked to me like you guys were looking in an anti-solar direction. Most comet hunters are looking on the horizon just ahead
no,
of
no, 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 no.
pre-dawn sun.
We're not looking in the anti-solar direction. We're covering the entire visible sky on a night from west to east.
Oh,
That plot just represented the number of discoveries, which are much greater in the opposition region. But we sure survey the low solar elongations. But we
So
cannot go under 50 degree solar elongation, and no professional survey does. So that is open. That's why you see so many Japanese comets like Iwamoto, Nishimura. Those are people with a telephoto lens surveying the sky at elongations lower than 50 degrees because we cannot reach that. So that is an open field for amateurs, for example. So if I was an amateur astronomer, I would search low solar elongation, morning, evening, especially morning, and Milky Way, because we don't survey the Milky Way. It's too dense. The images would look white, literally, from so many stars.
well, do you announce the regions of your survey so that other people can like look somewhere else?
Those regions, not only from our survey, but from Pan-STARRS and Atlas, they are public. In the Minor Planet Center, you can see exactly where a survey has been the day before, where it has surveyed. So you can see all of that in the Minor Planet Center. It's called something like survey coverage, like a submenu, subpage, and it's public data.
So I technically could be looking at a place that I know that you're not looking.
Correct.
Yeah, cool, thanks.
Yep.
And it sounds like there's still that opportunity with the daily minor planet data to discover something that wasn't, that you didn't have the time to look at. Is that correct?
The topic of discovery is a little, how to say it? Okay, so there is a very specific definition of discovery that the Minor Planet Center has, which is you are the first person to see an object during an apparition in which the object got a second night of observations, and there cannot be precovery observations. Okay, so that is a very convoluted definition of discovery, but that's what it is. So if you find something in the Daily Minor Planet Center, it won't be credited to you formally. It will be credited to the Catalina Sky Survey, but your name will appear in the official publications as co-measurer. If you look at Minor Planet Center circulars, you'll see that there's a section for observers and a section for measurers. So in my case, for example, when I'm working alone, I'm the observer and also one of the measurers. And it's usually the observer, the person who's gathering the data and reporting it in real time, measuring it. That is, takes like more, I don't want to say it takes more importance, but you know what I mean. That's like the person who found it, usually.
Thank you. Any other questions here in the room? And sorry, I know we have Omar and And Jerry and Ray on Zoom, if you have any questions, please
I
open.
have one question though. Do you get involved in any way with like using spectroscopy to try and determine the elements within the objects that you discover?
No, we don't do spectroscopy or colorimetry. No, we don't do any of that. We are strictly at discovery and follow-up survey. If someone else wants to do it, characterization. That's great, but that's just not what we get paid for.
Right.
You know, if NASA wanted us to do it, we will develop a system to do it. But it's, you know, they have other resources for that.
Thank you.
Any other questions? No? If not, Dr. Weirzchos, thank you very much.
Thank you for inviting me. It's been a pleasure.
We really appreciate the time and the information tonight. So thank you. We're going to move. You're welcome to stay with us, but we're going to move on to our general meeting topics.
No, I have to leave because actually I am running a telescope remotely right now. Like, I'm trying to conceal it, but I was running a telescope while I was giving the talk. So.
Oh, thank you for multitasking for us.
Sure, no problem.
Thank you. Have a good night.
Good night.
Good
All
luck.
right. You too. Have a good one. Bye bye.
Isn't that amazing? That I'm just amazed at movement in the sky. But that was great. Just as a side note, in July, we have a presenter who's going to be talking about the Vera Rubin telescope. He was actually the construction director for the Vera Rubin telescope. And so we'll probably get a little bit more information as well as to how they're working. And I will be prompting him to share a little bit of the imagery that's coming off of it, because they haven't published a whole lot. I don't know if anybody's seen much off of Vera Rubin other than the initial first light stuff. But gee, Eric, let's maybe move on to the announcements.
All right, let me go and share that screen.
And Jared, thank you for mentioning in the email reminder, our former member, Don Mockles, and the comet hunting, visual comet hunting that he did.
And he shared with us exactly where these guys aren't looking at. That's where he looked. And he found 12 of them in his career.
You know, and I wasn't part of the club when Don was involved, but how was he taking images and then looking? He was eyeballing. Wow.
Just,
Human plate solving almost.
yeah,
Yeah.
just like you have to know this guy really well.
Yeah,
And the part you know well, that's where you look.
that's amazing.
His memorized star fields is mind-boggling.
Yeah. Wow.
He was also co-creator of the Messier Marathon.
Okay. Yeah. Hey, well, from the Messier Marathon to this monster, so for 2 months I tried to solve this thing, and I never got it completed. And I'll tell you the truth, it managed to stay on an airplane the other night. So I was trying to finish it off on a flight. But did anyone manage to actually get the crossword puzzle done?
So at some point,
Here's-
just finish.
I know, yeah.
Here's the solution here.
That's not the solution yet, Eric.
Yeah, I'm sure.
Yeah.
I'm not running it for a third month.
You're not gonna roll
No.
it.
If you haven't done it yet, you're not gonna do it.
Yeah. Yeah, I tried twice. I got like 2/3 of the way through. And frankly, the 2 times that I was going to cheat, but I couldn't, I wasn't connected to the internet. The 2 times I was trying to play through it. So, okay. Well, I'll keep the stickers for this month then. Gee, Yeah, and Eric, if you want to torture us again, yeah, just, you know what, just flip it 180 degrees. We still won't get it. But next slide. I have to apologize because Tim, I lost your images and I don't know who else sent things to me somewhere along the line. I shared earlier, I've been flying a little bit too much. I had a little bit of turmoil going on in my life, and I managed to lose things more than usual. And I think I lost images. I lost Tim's. I know.
Mine's on YouTube, so you can
Okay.
find it if you find it.
Oh, okay. But and by the way, I missed the eclipse. So I went to the place where eclipses go to die. I was in Buffalo again and really got up, looked at the cloud cover and went back to bed at,
You
4.
can also find Tim's from our Facebook page. You posted it there too, right?
Yes, I do.
Okay, great. So thank you, Tim, for sharing that. And Eric, Doug, and Ray, great work. And I don't know if anybody else tried to give me a picture and I lost. So apologies for that. Yes, sir.
You tried to, I'd like to thank you for making a mistake, for making the rest of us feel a little more normal.
You all see these three photos, and you see the light, the luminance at the bottom of the moon. So is that something that's peculiar to this eclipse? Or are all eclipses?
It was low, so that's near the penumbra, the bottom part of it.
No eclipses go perfectly dead center, so I also got one side that's a little bit.
Oh, the moon wasn't always in the umbra at one time.
No, it's not dead center, it's just closer to the penumbra.
Oh, I follow you, okay.
So the darker area is closer to the dead center of the umbra.
There's a
The
little,
top.
there's a little corona shining around the moon. If you're not dead center, then that side tends to have more corona.
And the reason mine's fuzzy is take with a cell phone, just click.
I thought it was because you were tired.
Huh?
I thought it's because you were tired when you took the picture. They were just fuzzy. No?
The cat woke me up. I thought, okay, I got up to take a pee, and I thought, let's go out and see.
Yeah. And then the next slide, our new moon challenge. And again, if I lost pictures, I apologize. But Casey and Tim, I got yours. And did I cheat anybody out?
Ray sent one in, didn't he? Did
I
Ray
don't
send
know.
one?
Ray, had you sent one in that I lost?
You-
Oh, you're on mute if you,
What
but
was this a planet right here as well? Wasn't there a planet nearby the moon that night?
It might have been, or might
Probably
have been
the-
dust on my lens.
and Casey, you didn't try to steal anybody's logo
Yeah.
this month. And if you go to the next slide, Ray really knocked it out of the park with Thor's helmet. That's,
Nice work, Ray.
yeah, fantastic image, Ray. And I'm kind of happy, the Sombrero Galaxy, I'm thrilled to see that come up. That's the first object that I think I actually saw in 1992 through my original telescope. And I think Jeff helped me find it. So,
I think that was one of the first galaxies I saw at college as well. When I got into astronomy,
yeah.
the Sombrero.
Yeah, I like these. I think these are great reminders of what's there and available, and what we could be doing. If you go to the next slide, just a reminder of the Messier Marathon, and Jeff, thanks. I stole this out of the newsletter. I've never attempted the Messier Marathon. Yeah, I was going to ask who's actually completed the Messier Marathon in the past. I'm imagining you have, Jeff.
I'm 30 during a marathon.
Oh,
I can't say I've gotten all of them, but I've only gotten 100.
okay.
I've never gotten that 30 during a marathon.
I don't have the patience, frankly. But yeah, in the newsletter, Jeff gives an outline on, you know, the kind of the target windows, the 14th and the 21st. 21st is the hasp. So there's, the
So the hasp is the 14th.
is the 14th?
Yeah,
Okay.
I think so.
So yeah, there is an opportunity to try to get as many as you can.
Yeah, late March is when the sun's in that yellow spot there. And so that theoretically gives you about a 2 week period of time where all the objects can be seen with the sun far enough under the horizon where it's dark enough to see. But I think it's crap because I've never seen M30 on a marathon. It just rises in that morning dawn. It just invisible.
Yeah. And if you go to the next slide, so, you know, it's funny when I was writing my note for the newsletter for the month, I didn't know who our speaker was, but I had actually had his Comet on my watch list. So, and it's a little tough to see here, but these are March 6th, 7th, and 8th. So from Tracy, and I went out and I imaged the comet. The tail is actually pointing in that direction. This bump out shows it a little bit better. Some of the blur from the four tails, apparently. But this was a 32-minute image. So I was trying to track motion. So I went back the next night at roughly the same time and did 50 minutes. I think this was the roof of my house. But, and then went out the next night and did another 30. So that was actually the motion, stacked the pictures to try to get an idea of distance or how far it had moved over that period of time. And so it's kind of neat because you can, I think I was, now, shoot, I'm going to quote it wrong. I think it was about magnitude. No, I don't remember now. It's dimming as it moves through the sky. So if you go to the next slide,
It's moving out, back out.
yeah, it's moving out right now. So the next slide gives a little, is it the next one? It's the next one. No, okay, I left out, okay. So it's actually from the southwest, it's actually traveling up between Orion and Taurus towards Aldebaran right now. And what it's going to do over the course of this month, it's as it's moving out, it's tracking up through the sky, and then it'll drop back down again. But it is visible. I want to say that it's around magnitude 8, 9 right now. It'll get to about 10 when it gets up towards Aldebaran, and then it really fades off. So it's,
What exposure time did you use for that?
pardon me?
What exposure time did you use for that?
That was with the dwarf, and that was it was 30 second, yeah, 60 gain,
Okay.
and then that time period. So it wasn't the best location for it, my backyard, but it was more of an experiment.
Yeah.
So the next slide is the announcements. March 19th, New Moon Challenge. Look at my notes. I had some of their stuff written on here. But, and then the 14th through the 21st, the Messing Marathon. And so I had the 21st for a pass.
Yeah, I think you are correct.
Yeah.
I'm mistaken. It was doubled up with the
right.
Astronomy in the Park, I think.
Yep. And then I stole Doug's April 1st full moon. Our general meeting, off the top of my head, I don't remember who our next speaker is on the April 9th is
We won't actually be in Chartville 1 though, right?
Oh, no, how did I get that under? Sorry. It'll be in
It'll be
this
here,
room.
yeah.
We'll be in this room again. Apologies for that. Oh, I don't, yeah. But it's, his last name is Davila. Talking about the search for life on Enceladus. So he's part of the NASA cadre of folks. Highway 4 Campo Seco on April 11th, 17th, new moon with the new moon challenge, the 18th. April 25th, mark your calendar because it's astronomy in the park and our potluck. What I don't have in there, and Doug, sorry, I zoned on it, but there's a handful of, in fact, if we go to the next slide there's a lot of outreach stuff going on. So this is what we, in the last couple of weeks, the 21st group of us were at Lodi High School for their STEM event. And then astronomy in the park. And in between all of that, Doug was actually giving another presentation. So I think Doug did probably a 7 to 11 p.m., 7 a.m. to 11 p.m. Day. April 25th. Yep. And then March 5th, we were at the Commodore School for a STEM event. And really across those, thanks to Hervé and Casey and Rich and Bill and Eric and Doug for making that happen. And Doug still, Doug is always looking for help with the STEM events. And just as a quick rundown, March 23rd, we have an event at St. Bernard's School. I'll be there. I could use a body or two to help. March 25th, we're at the Rosa Parks School that had been in Stockton that had been rescheduled. April 15th, we're at Villalobos School. That's going to be more of a classroom thing because there's nothing high in the sky. So I'll be there for that one. For the 15th, I probably don't. Yeah. And then April 19th is the Earth Day event in Victory Park.
Lots of help.
Yeah.
There.
And then back to the 25th with the astronomy in the park and the potluck.
I think we skipped the one at Lincoln High. That's the 21st, right?
So,
We skipped the one at Lincoln High School.
Yeah.
That's the 21st.
Oh, yeah, that's, yeah.
this coming like a week from Saturday, a week from the Saturday.
Yeah.
Casey, Eric, Bill, Pat, will be out at Lincoln. And we could really use another person or two out there.
With the solar, we'll have the solar scopes for that.
He said that she will be out there.
Okay.
Okay, so you have 4.
Do you know if she has a solar filler?
No, she does not. Casey's got the demo striking spark scope with that filter.
Okay.
And if Kirby is there and wants to use her scope, that filter will work. That you can just use our sharp spark scope as a static display.
Okay.
Or the moon, or
That would be this 4 solar stuff.
When is that?
was that
Pat, are you bringing,
week from Saturday, 21st.
at Lincoln, are you bringing the solar scope?
Oh, yeah.
We'll have your 2 here,
I'll have mine, yeah.
so that'll be 3 plus the one.
Right.
I even practiced with it, so I know how to use it.
Tuesday, there was that other school event from Mona. There's one Monday, one Wednesday, is before Rosa Parks. You're gonna confirm, I don't know.
Yeah, it's Rosa Parks. So.
No, before, there's Tuesday.
I think Doug, that was the one that you said no to.
Yeah, that,
Oh, because it was gonna have to be a classroom.
Right.
Or start.
that one was in the set, right?
Yeah. Hey, and just, I don't have a slide on this. In fact, you could go to the next slide because it's the last slide.
Yep.
But before we even do that, just a heads up, this building is going to go under construction. We're trying to figure out when we get displaced from this room. As we stand here right now, we've been told that we have the room booked through the end of December. But the construction, parts of the construction begin earlier than that. We can't get a clear confirmation yet whether or not we have internet access in the room. If we don't have internet access, all of our speakers are on Zoom. So we've got a different problem to solve. So we're scrambling right now to try to figure out, this room may be available, the internet might be working. If it isn't, one end of the continuum is we find another location. The other end of the continuum is we do Zoom only meetings, right, until we can find a spot that we could congregate. So we're working on that right now. I've been talking to the Hagen Museum. There's some libraries on our list. There's a couple of different venues that we're trying to get in some form of an agreement so we have a place to go. Because I'll tell you the truth, I'm a little the construction here was supposed to start in July initially. They've pushed that to December for this room. But I'm a little uncomfortable because what I don't want to do is have us walk in here, for the July meeting where we've got the director of the Rubin telescope to present to us, and we don't have any way of communicating with them. So we're kind of scrambling right now. If anyone knows of a public venue that allows this type or enables this type of activity, let me know. I'm happy to go beg and bribe to try to find a spot for us. But what I don't want to do is I don't want to have us get stuck. So if we don't have a room, if we really end up in that position where we don't have a place where we can count on the internet, we may have to just do Zoom-based meetings for a bit. Truthfully, so this building will go under construction. We have the opportunity to rent a room, to pay for a room somewhere else on this campus. So we're looking, that's an option. Moving is another option. Frankly, if we had to break into our coffers a little bit and pay for a room, there are some opportunities for us. So we're just exploring everything possible. But if anyone knows of a location that we could use, let me know. And we'll, want to make sure that we don't lose the opportunity for us to get together. Zoom meetings are okay, but I like getting us together anyway. I don't want us to be an okay group. So, that it? Yeah, I think that's it. So yeah, next month is Alfonso Davila from NASA Ames Research Center on the search for life in Enceladus. Heard him talk. His talk is pretty darn good. And I think that's, unless anybody has anything else to share, I think we're done for tonight. Oh, yes.
The RASC handbooks we ordered, we have one left. I do not believe the person who ordered it is interested in picking it up. So $26 we paid for these. And we have one available if you want it.
And it was the special $26 Jerry bargain price. So yeah, you get a deal. So okay, it's time to go home. I need my space. By the way, this was a Christmas gift from one of my daughters, and I can't tell you which one because I don't remember. Yep. Thank you all very much. Oh wait, I'll make it official. Thank you. Good night.
Did anybody else see Venus and Saturn yet?